Hi everyone, and welcome to this short video about determinants. In this video we will talk about determinants and how to calculate those and how they are related to the concept of invertible matrices. We will also cover several examples for several different rules and sizes of matrices so that you can train your new knowledge. With that being said, let's start. In the last week, you already learned what an invertible matrix is. And we found out that it is really interesting to know whether a matrix is invertible or not. And also remember that only squared matrices are invertible. But now, regarding the invertibility of a matrix, we kind of want to easily know how to see if it's invertible or not. So a question is, when is a matrix invertible and how can we easily determine if it's invertible so that we don't have to do the whole process of inverting it for then finding out that maybe it is not even possible? And the answer to this problem is the determinant, because the determinant of a matrix directly tells us whether it is invertible or not. Before diving into the calculation for a determinant now, and before covering the different rules, I want to clear several things now. For a squared matrix M, we write det M or det in parentheses M, or the vertical lines with the M in between for the determinant. And when we calculate it, we are interested in the value, of course, that comes out. If this value is not zero, this means that our matrix would be invertible, and if it is zero, the matrix is not invertible. So we are only interested in whether the determinant will be zero or not zero. So now you know all the necessary background information. You know what the determinant will tell us and how we need to evaluate the result. So now we can dive into the calculation process. First of all, let us start with a 2 times 2 matrix. For a 2 times 2 matrix, which we can write like A, B, C, D, we define the determinant as A times D minus C times B. You can see this marked in colors here. So we start from the top left and multiply it with the bottom right, so A times D. And we take this positive, which is why it is a plus there, and then we subtract C times B. So the bottom left with the upper right. Here I prepared 2 examples for you, so you can calculate the determinants on your own. You can simply use and apply the rule from the previous slide, and then we will also go through the solution step by step together on the next slide. And you can also already think about whether the matrix would then be invertible or not. And this, if you remember, was covered in the beginning. So if the result is not zero, then the matrix is invertible. And if it is zero, it would not be invertible. Here you can see the solution for the 2 tasks. For the determinant of the matrix A, we multiply 2 times 3, so again the top left with the bottom right, and we subtract 5 times 4, which is the bottom left times the top right. And this is 6 minus 20, which is minus 14. And as this number is not zero, this means that matrix A is invertible. For matrix B, we can do the same for the determinant. Here this means we multiply 0 times 2, and then we subtract 1 times 1, which is 0 minus 1, which is minus 1 in total. And again, this value is not zero, and therefore matrix B is also invertible. So by now you should be familiar with how to calculate a determinant for a 2 times 2 matrix. And this should not be too complicated. So let us continue with different cases now, with bigger matrices. For a 3 times 3 matrix, the rule for calculating the determinant is a bit different. Let's assume we have a matrix M, here written as A, B, C, D, E, F, G, H, I. And then the determinant is defined as A times E times I plus B times F times G plus C times D times H minus C times E times C minus H times F times A minus I times D times B. Wow, this looks complicated. But actually it's not too complicated because again, we can use a similar rule, so we can draw in lines that help us finding out what we need to multiply. And this is exactly what the rule of zeros tells us. And what we do is what you can see on the bottom here. So first you write your matrix, which is on the left side here, and then on the right side you copy the matrix again, but you leave out the last column, which is why we added A, B in the first row, D, E in the second row, and G and H in the last row. And then again you can draw in the diagonal lines, and again from the top left to the bottom right it's then the positive ones, so you add these ones, and in the other direction you subtract them. So you have 3 times positive ones and 3 times negative ones. And if you pause the video maybe for a second, you can really check that these are actually the letters that are in the formula from above. So this is a really nice kind of helper rule that easily gives you the solution for the 3 times 3 matrix. But let's look at some examples now and apply this in practice. Here you are given 2 matrices again, this time 3 times 3 matrices. You can use the rule from the previous slide to calculate their determinants now. And again, you can already think about whether the result tells you whether this matrix is invertible or not. And here you go with the solution to the 2 exercises. You usually always use the rule of zeros to help you determining it in a nice and easy way, which is why I also wrote it here with this rule. So you write the matrix and then you copy the first 2 columns. And then you can nicely draw in the diagonal lines and then simply multiply the things that are within one line, with the red ones then being positive and the blue ones being negative. So for matrix A, this means we multiply 2 times 4 times 1 for the first red diagonal line, then 1 times 2 times 3 for the second one, and then 1 times 0 times 2 for the third red one. And then for the blue diagonals, we do 3 times 4 times 1, and we do this negative, then 2 times 2 times 2, again negative, and then 1 times 0 times 1, negative. And in total, if we add this all up, this will yield -6. And as -6 is not 0, this matrix is also invertible. For matrix B, we do the same. So we write down our matrix. We write on the right side again the first 2 columns of the matrix, and then we draw in the diagonal lines. And there we would have 3 times 2 times 4 plus 4 times 1 times 1 plus 2 times 1 times 2 minus 1 times 2 times 2 minus 2 times 1 times 3 minus 4 times 1 times 4, which would be 6 in total. And again, this is not 0, and therefore the matrix is invertible. So by now you should know how to calculate the determinant for a 2 times 2 matrix and for a 3 times 3 matrix. These are also the matrices that you will probably need to calculate by hand, or you need to know the rules by hand. But of course there can also be bigger matrices, and therefore we will look at how to solve it for any random n times n matrix now. If we have an n times n matrix, the whole process of calculating the determinant is a bit more complicated. But again, there is a formula for it, which indeed looks a bit complicated, but we will go through it together now. So we have a matrix M, which is here in the definition defined as Aij, Ij, which I'm not sure if you're familiar with this by now, but the I stands for the row and the J for the column. So this is kind of the indexing of our matrix. And this matrix is now a squared n times n matrix. And for every I that is in between 1 and n, the matrix Mi now is defined as a n minus 1 times n minus 1 matrix. So it has one dimension smaller and still squared. And it's the same as the original matrix M, but we leave out the first column always and the eth row. So you need this because we will use it in the formula now. And now the determinant of M, of our original matrix, can be defined recursively. So what we do is that if n is 1, then the determinant is simply A11. So it's the entry at that place. And if not, we do the sum, which is written down there. And behind you, so on the last part, you have the determinant of Mi. So you kind of make it smaller recursively every time, and you multiply this determinant of Mi with AI1, which is the entry of our matrix from the first column, so the one that you crossed out for the determinant, on the position of the row that you crossed out. And in front, you always multiply it by minus 1 to the power of I plus 1, which means for the first row, which would then be, so the first row has I equals 1, so it's minus 1 to the power of 1 plus 1, so it's positive. So for the first row, it's always multiplied by 1, then for the second row with minus 1, and then 1, and then minus 1, and so on. So I think this sounded a bit confusing and complicated, and therefore we will go through an exercise together now, because this will visualize it a bit more, and then hopefully it will become clearer what this formula means. Let's consider the following matrix A, which is now a 4 times 4 matrix. With the formula from the last slide, you could calculate the determinant now. And you can try to do this on your own, but if you're not so familiar with the notation of the formula yet and not sure how to read it, don't worry. We will go through it step by step on the next slide, and I will explain in detail what we do with all the different parts here. Here you can see the solution and the intermediate steps for determining the determinant of the matrix A. So in the end, we will come up with the value minus 5. And as the determinant of A is minus 5, which is not 0, this means that this matrix is invertible. But now onto the steps that we do. You can already see a lot of color coding, which looks a bit confusing, but we can tackle this. So from the definition, you already saw that we had to do this kind of recursion, and we want to make the matrix smaller, because if it's smaller, you already know which rules you have to use to calculate them. And you know this, for example, for 3 times 3 matrices. So recursively, we can do it until we end up there, and then we know how to calculate them. And what we do, what was done in the definition, is that you, for the determinants that are smaller that you want to calculate, you cross out the first column, and then always one of the rows. So for the yellow one, which is the first one in our formula, we cross out the first row and the first column. And then what is left is this matrix 2, 2, 3, 1, 3, 2, 1, 4, 2. And we multiply this with the first value of the first row. And for the orange one, you do the same. So you take the second value of the first column. So we kind of use every value of the first column once, basically. And then you take what is left, but cross out this one line, this one row where you took the value from in the beginning, so that you have a squared matrix again. Which means that for the orange one, we have the value 1 in the beginning times 0, 1, 1, and the second row, this 2, 2, 3 will cross out, and then we would take the 1, 3, 2 row and the 1, 4, 2 row. And for the pink one, we do the same. So we take the 0 from the first column, and for the rest of the matrix, we cross out this row where the 0 comes from. So we have 0, 1, 1, 2, 2, 3. The row with the 1, 3, 2 we cross out. And as the last row, we take the 1, 4, 2. And for the blue one, we do the same again. And then you always multiply in front what was also given in the formula, a 1 for the first row, so for the first thing where you cross out the first row, a -1 for the second one, then a +1 again for the third one, and then a -1 for the next one again. Okay, this sounded a bit complicated, but I hope that the color coding helps with what happened here. And now you can use the usual rules for a 3 times 3 matrix to calculate its determinant. I didn't write it all down here, but you can use the rule of Serres here. And what you will end up with would be a -1 for the yellow part, then a -1 for the whole orange part, a 0 for the pink part, and a -3 for the blue part. And in total, this would then be -5. And that's already it with this week's video about determinants. By now you should know what a determinant is and for what we need this value. You should know how to calculate the determinant for a 2 times 2 matrix and a 3 times 3 matrix quite well. And then you should also be familiar with the rule for an n times n matrix, however you don't have to know this rule by heart. I hope you liked this video and hopefully see you sometime in the future again.